two of our colleagues in the House from the Planetology and Habitability Department. Jens, he has a PhD in geology by the Stockholm University. He developed his studies both in Sweden and in the USA. And he first joined the CAB back in 2002 as a Ramon y Cajal researcher, after a Marie Curie postdoc at the International Research School of Planetary Science in Italy. He's in charge of the Impacts Laboratory here at CAB, where he has created a world-unique laboratory for wet target impact simulations. And Isabel, she is astrophysicist, sorry, and a PhD in computational fluid dynamics, both by the Universidad Complutense de Madrid. Her expertise lies in the development of mathematical and numerical models applied to complex problems of continuum mechanics with applications in planetary science. They are both members of the DART investigation team, as well as core members of the Hera mission impact simulation working group. Today, they will present us some pieces of their work in this field, which has the title of Experiments at the Experimental Projectile Impact Chamber at CAB in support of the DART-Hera space missions. So, welcome.
Yeah, I can take the mic here, and I wanted to say welcome to all of you, and also don't hesitate to break in during this talk. We really want this talk to be quite open and easygoing here, and so don't hesitate and sit and wait to the end or so. If you see something you want to ask her, but just ask us. Isabel will begin a little bit general about the DART, and I take over later.
Hi. Okay, so I'm introducing the DART mission first, and later on, Jens will speak about our work here.
9, 8, 7, 6, 5, 4, 3, 2, 1. Liftoff, Falcon 9 DART on NASA's first planetary defense test to intentionally crash into an asteroid.
Okay, so I don't know if you were aware of that, but in November 24th, the DART mission was launched, and now is in space on the way to Dimorphos. The goal of this mission is hitting in the moonlet of a binary system of asteroids, with the aim of deflecting the smaller one and changing the orbit of this one. Okay, so that this change can be measured afterwards from Earth, from the telescopes. So some years after, in 2026, another mission, this time from the European Space Mission Agency, will arrive to Dimorphos and will check what happened with this impact. Okay. So we have, well, we wanted to present this video, which is quite illustrative of the aim of the mission. This is the DART spacecraft hitting Dimorphos. Is very small compared to the, well, this is not really scaled, but the spacecraft is small compared to the asteroid. And after the impact, we expect that since this is depicted here, the orbit will change in about a small percentage, about 1%, more or less. And we will see this change in the observations from the Earth. Okay, this slight change, which is only 1%, is going to be more or less 10 minutes in the orbit. Nowadays, the orbit is about 12 hours, and the change is expected to be in just 10 minutes, but still enough to be measured from here. As I was saying, this is a international collaboration between NASA and ESA. So DART is a NASA mission, but is in collaboration with ESA's mission Hera that will go to Dimorphos later on to check the result of the impact. And why this? Why this mission? And why all this fuss about the asteroids and all these kind of things? Well, the thing is that meteorites are bombarding Earth continuously. We can see here a map of all the meteorites bombarding the Earth since 1988 to now. And well, we have different colors depending on the size of the impact. But we can distinguish here, for example, between 3 different sizes. For example, an impact of the type, the mouse is not, yeah.
No, you use the.
Okay. Well, an impact of 20 meters, like the one that occurs in Russia some years ago, just happens every few decades or centuries, but even these small meteorites can cause a big fuss. You know, we will see later on the result of something like that. This one in Tukunska is even worse, but this is hopefully happening only every few centuries or millennia, so the risk is a little bit less. And of course, this one, like Chicxulub, which is the dinosaur killer, only happens every 100 million years or something like that. But of course, if once happens, the result is devastating. Okay, so
65 million years ago the last time. So
yeah. So well, I never knows, because maybe now is the time for the following. So yeah. That's why some years ago, it began an international network for controlling or somehow discovering this kind of NEOs, near Earth objects that could be a potential hazard for humanity. Of course, the biggest ones, all of them have been already discovered, or we think so. But the problem is that obviously, the smaller ones are not so easy to detect because, you know, they are very small, they are very far, and it's not so easy. So for those ones, what happened now? Here, it's not so easy to manage this thing. Okay, so for these ones, for example, between around 20 meters or 25 meters or so, most of them has not been discovered yet. And the problem is that a meteorite of this size could be a real problem in case it falls here on Earth. We have an example here, which was presented in this conference. It was a 60 meters meteorite, and a 60 meters meteorite falling on New York would erase completely Manhattan from the map. Okay, so even the smallest ones or the smaller ones are a big hazard for humanity. So now it comes the priority of designing a plan and the technology to be able to deal with this kind of risk. So here we have a graph in which, in the x-axis, we have the warning time. I mean, this is the time in advance for which we will know about the possible impact, the possible meteorite. And here we have the size of the meteorite. Okay, so depending on the size and the warning time, different techniques could be applied in order to be able to avoid the disaster. Okay, for a diameter similar to Dimorphos, the most feasible system would be using a kinetic impactor. That means that this is the aim of the mission. The mission is a test itself. We are going to test if, in this case, if a meteorite of this size, more or less, came towards the Earth, and if we knew it enough time in advance, if it would be possible to stop it, just not stopping it, but deflecting it, just impacting on it without using any kind of weapons or something like that. For bigger meteorites, of course, a kinetic impact is not enough. We wouldn't be able to do anything with that. In that case, it would be necessary to use nuclear weapons or other kind of, I cannot imagine with kind, but just a kinetic impactor wouldn't be enough. So here we have a little scale comparison for imagining how Dimorphos and Didymos are. Dimorphos is more or less the size of the Great Pyramid, and Didymos is more or less between the World Trade Center and the Burj Khalifa. So they are small enough, especially Dimorphos, small enough for us to be able to move it just with a kinetic impactor, but still big enough as to make a big mess if something like that could hit us on Earth. So we have depicted here the 4 goals of the mission. The first one, of course, is impacting Dimorphos. If the impact does not occur, the mission is gone. So this is the first thing. And afterwards, we expect a change in the orbit, at least of 73 seconds or bigger. Indeed, we expect around 7 minutes, okay? But it depends on on how things go, you know, the properties of Dimorphos that we don't really know very well, and all these kind of things. So, well, we have a big margin here for this change. But the idea is being able to measure this change using the observatories here on Earth. Well, the fourth aim is measuring beta. In this mission, we call beta to the momentum exchange, okay? Because knowing the momentum exchange, we get a lot of information about the change in velocity, the change in direction, and also the properties of Amorphous. So this is like the last goal. To explain a little bit more what is beta, what is here? Yeah. If beta is around 1, that means that there is no ejecta at all. What is the ejecta? Well, when the DART spacecraft will hit on the Amorphous, depending on the characteristics of the Amorphous, there will be some ejected material coming out from the impact. If imagine the Amorphous is very rocky and we don't get any ejecta at all, then beta would be just 1. In this case, the change in momentum is going to be very small, and then the change in the orbit. If this ejecta is a little bit bigger, then maybe beta is around 2, and then in that case, we have a moderate ejecta emission and a moderate exchange of momentum, okay? In the last case, in which beta is very big, we don't expect this is going to happen, but anyway, in this case, the ejecta would be very, very big, and the change of momentum would be also very, very big, okay? Of course, this parameter beta depends in largest extent on the properties of the asteroid itself. You have here different pictures. For example, If you have no porosity at all, the value of beta, we have, well, in the mission, we have been calculating beta for different cases. For this case with no porosity, beta value will be 1.32. If we have microporosity, then this beta is around the same value, more or less. But if we find, for example, a rubble-pile asteroid, which is what we expect to be Dimorphos, then the beta value is a little bit bigger. Anyway, if you see here, beta is around 1.52, no more than that. Okay, what is a rubble-pile? A rubble-pile is a kind of asteroid in which we have a mixture of rocks and regolith. Regolith is a very fine sand between the rocks. So it's kind of an aggregate, it's heterogeneous, and indeed, what we don't really know which amount of regolith in comparison with the rocky or so. Okay, so this is something that has to be determined with the DART mission, because up to now the knowledge about Didymos is very scarce. This is how we have modeled with the shape of Didymos with combined radar and so with observations. As you see, the image is very, very poor. And this is the big one. What about the Amorphous, which is our goal? Well, we don't really know anything. We don't really know, anything about it. We have here a question mark because we don't know which is going to be the shape. So for the modeling in the mission, we have been using all these different kind of shapes. What is this? Again, the mouse is gone. Okay, here. A sphere or something Herreros-like or Cleopatra-like or something like that, different shapes, because we don't really know which is the shape. We don't really know which is the composition. We guess it's a rubble-pile, but nothing else. And so, well, that's why simulations and experiments are so important for this mission, because it's a way of knowing a little bit in advance what is going to happen and be prepared for that, because we are not going so much time in advance before the impact. So this is exactly the motivation of our work. We have been here at CAB performing some experimental work with two aims. The first aim is validating the codes that are being used for the mission, and also to try to understand how this heterogeneous material would behave after the impact. Because, the models are models and they go to a certain level, but at the end, you need also an experiment to check what is happening there and to be able to understand what is going to be the dynamics of the system and so on. So this is the thing. Okay.
Okay, so we begin. I will. So as Isabel said, we are combining our impact experiments in the lab we have here with numerical simulation. We are providing data from the experiment to these model developers, and so they can understand how the codes work. The codes work for different properties. So we can so they tell us test this, and we test these different properties in the target, and then they put it into the code and see what new thing we need to test for the next step. And in the end, we will be able to apply this on a more advanced model of the actual impact on the Dimorphos itself. So you may have been to the lab in the far end of the building here. This is how it looks like. We have this cannon, compressed nitrogen cannon here, and we can shoot at different angles. In these cases, we have been shooting vertical, not as this photo there. And for the first test, we were just testing homogeneous materials of different densities, and we could see that the numerical model would fit very well to the experiment. So in this case, we could move forward into more, little bit more complex targets. Similar, we are making layers of with different densities of these granular materials, and we can see there again that the numerical models are producing results that are very similar to what we get in the lab. So we are on the track for going further. And I have this, maybe I need to stand here. Yeah. So we have to then, so we can go on to this more complex target of heterogeneous materials. And in this target setup, I would prefer to stand there if I was allowed to. With the and so we have a more complex target here. We create a rubble-pile, really, in this. Now here it changes also when you press the mouse. So we create a rubble-pile target with these porous ceramic balls embedded in this sand that we have here. And you can see this, we are shooting in something called quarter space. That's you have a cross section for the camera to film here. We shoot along the glass of the tank, and you can see these layers of, layers of these ceramic balls embedded in the sand here, and how they are positioned in the target. And here I want to make something ever more complicated. I want to escape, go into there. That's this thing. And now I want to show you how this experiment looks like with this complex. Closer. Okay, I thought it was that was making the round to go around. So what you will see now is the high-speed camera experiment of this, and it froze. No. Can we run it from the start again? This was not. It's doesn't want to participate, of course. See why it is so jumpy. So well, nothing is easy with this. At least we got a film from it. That's not always, because it's really complicated to get this thing to work there. But there you see, now I think it's running a bit smoother. You saw that the initial process of the impact itself is really, really quick, but with this high-speed camera, we can move frame by frame, and we can really analyze this in detail on how these heterogeneities in the target are affecting the cratering. So you can see how these ceramic balls are now flying out and how they interact with the ejecta curtain. We can see what the angle of the ejecta curtain we get. And all these things are important for these calculations of the beta as well. So we can stop this and go back to the talk. There. This one, right? Okay. Now we're going to start to strip this down into details. So here we are coming with the ball quicker there. We're striking the target, as you see. To the right, we have this numerical simulation, 3D numerical simulation of the experiment. And we can see how the crater is developing. We get information from this on the dimensions of the crater, the shape, and we can fit this with the numerical simulation. And we can see also that the numerical simulation of this with all the various inputs gives a crater shape that is very similar to what we have in the lab. So that's a good first step to know that what we see can be useful. This is a resulting crater seen from above. We have these ceramic balls. Some of them are ejected on the rim, others are ejected to greater distances. You can also see that the ejecta is creating rays. With this overlay, we can see which ball moved where. We have numbered the balls. We can also see how the balls are moving during flight and things like that. But we have this question here. What happens if the impact would strike on the limit between a more boulder-rich area and a more fine-grained area? Would we get a complete different shape of the crater? Would that affect this beta and maybe causing spin of the asteroid after the impact and things like that? So we set up a target like this. We are having identical to the previous target on one side and just homogeneous sand on the other side. And we are shooting there. And we can now see how this thing is developing. You can see already now that there is a difference between the side where there are embedded boulders, the rubble-pile side, and the homogeneous side in ejecta angle. And in the shape of the crater, you have a steeper crater, a little bit steeper on that side. And then it's just details. We move on. And here again, we measure the position of the balls, how far they were flying around it. You can see this one ball there was actually this one is not really working. No, now it's alive. You have to shake it first. Yeah. So it ends up here on the rim, but it rolls to that position. And we will come to that, what happens in the numerical simulation later on here. We investigate this in cross-section. This is just details also, but let's see, there you can see on this side, the layers are behaving differently from that side. And so all this is important as inputs for the numerical simulations. Okay, we can at least directly see that there was no risk that there would be a great difference between the crater from one side to the other if the impact struck on the boundary between these two types of targets. And we are investigating also with this what happens because we have a ball on the impact side, a boulder that gets completely crushed. Will that consume energy from the cratering itself? And this is also something we are studying with numerical simulation. And for knowing, of course, what happens with this boulder-rich target, we must also make a reference experiment in just pure sand targets. So that is this crater we form here. And overlaid on this now, we can put the first one, you saw that was complete rubble pile target, the yellow line here. and also the one that was half and half. And you can see that on how the rubble-pile target definitely have a smaller and steeper crater like this, but a little bit deeper, but also much different in the ejecta angles of this. But interestingly, the experiment 2 with the half and half target, you can see that it is a more or less perfect fit on the sand target side with the pure sand target, and not perfect, but at least the rubble pile side is towards the rubble pile, complete rubble pile first experiment, what you see here. So it's in between the two types of targets there. Then we move on. And you can see that the final craters are also very good fit. We can see that there was no ray formation in this very homogeneous target. So we see that there is very good fit between the how these two various rubble pile targets developed, and the boulders in the target seem to affect the excavation and ejection of the material. This, I like very much this slide. This is just fresh out of the bakery. We submitted it yesterday now. This is the final result of the numerical simulation, the 3D simulation. What you see here in the lower side is the 3D simulation of these two experiments, the complete rubble pile target and this one that has half and half target. And you can see that in the experiment where the balls were landing, it's basically a one-to-one fit between the numerical simulation and our experiment. And this ball, hey, why is he going like that? This ball that landed on the rim here is that guy there, and these two guys were not lifted completely up on the rim, and they are not so in the numerical simulation as well. So the numerical simulations are really on a right track, probably for being able to foresee what's going to happen. And we have this reconstruction on how the balls are moving, the boulders in this rubble pile target. So this is the summary slide, I think is the last one. So the simulations are definitely needed to predict the behavior of Dimorphos from the DART impact, but also for the analysis of the Hera data. The Hera mission is going to arrive later to study the crater itself, to really get more information on what really happened with the DART impact, not just the change of the orbit of the asteroid. This to model this kind of complex target is very computationally costly. So it's very good if one can also use experiments for this. It's faster to repeat these things in the lab than in the numerical simulations. What we could see though is that the lab impact successfully validate the codes aimed to simulate the DART impact. The target layering generates concentric craters depending on layer thickness. So layering affects the crater shape and how the ejecta is moving also. Shots into rubble pile analog targets are closely reproduced by this SPH 3D simulation. Boulders in the target, now I lost it, shake it. No. Ah, there he is. He comes, sometimes he comes. Boulders in the target affect ejection, crater shape, and lowers the momentum transfer. This is also an interesting outcome of this study, because it affects also this ejection of material, which is going into the beta, as Isabel showed. So this is an important outcome of our experiments here. And also, when not hit by the projectile, boulders are displaced or ejected and not fragmented inside of this crater. And this is something that has been seen also in studying of the large-scale experiments on impacting on other asteroids, like on with this Hayabusa 2 impact. They also saw that boulders were behaving similar to how they behave in this lab here, and also how this boulders are creating patterns, ring patterns around impact sites, and so just like has been observed on these other rubble-pile asteroids like Ryugu and Bennu. So we stop there. Any questions?
Thank you. Very interesting talk. I don't know if there is any question in the room. I go there now.
Hi, very interesting work. I was wondering if you could comment on how the asteroid composition is usually determined, because you explained that we know very little about Dimorphos, but maybe some other asteroids are known a little bit better. And except for the Tsurium of Gerasimenko. And the second question is whether the composition of beach sand and the balls, how close you really think they represent a rubble-pile? Because of course I know nothing about this, but I would expect an asteroid to be a bit more compact than the sun. So yeah, and I think those are my questions. Thank you.
Okay, so for the first question on how to know about if an asteroid system like this is rubble-pile or not, one can see when the small asteroids like this, if they have a satellite around them like this, it's often a consequence of a spinning rubble-pile asteroid that has been releasing material out. It's spinning due to this Yorp effect. When the sunlight is hitting one side and it's creating a spin. And then this material, you can see how it's like a centrifugal force, and it's releasing out a little moon. This moon remains for some time. It's around. It can later be separated more and more after I think it is not so big span. It's hundreds of thousands of millions of years, something like that, when it starts to be released. But that is basically an academic guess. Best guess is that when smaller asteroids like this have a satellite like this, it's often because of that they are rubble piles like this. Any more comment on that?
Yeah, besides the DART mission, there is a group, which is the observers working group, which is basically astrophysicists working in the observatories and so on. By spectroscopy and these kind of things, they have determined the composition of, more or less, the composition of at least Didymos. So this is also a clue, because, you know, albedo, spectroscopy, and all these kind of things, they have considered that it is probably most likely a rubble-pile. So, yeah.
And then the second question is our choice of materials. We know something from the studies of from the Hayabusa missions and so of the Bennu and Ryugu asteroids on the properties of materials on them, and the numerical modelers were giving us frames on within what type of properties these materials should have that we were using in the lab. So the choice fell on using these boulders of ceramic boulders of a certain size, preferably similar to the size of the projectile in this case, because it was simpler for them to begin with the modeling, and also with density and strength that is estimated to be similar to what we know of boulders on these other rubble-pile asteroids. And funny was that the best fit was to use filter balls for aquariums. So that is what we have used in this case. And then we have embedded it in this beach sand that we have well constrained properties of from before. Yeah, and also with the compaction is important there. So we are working on with maximum compaction in these experiments, just to have best properties of that material. And then you put it into the numerical simulations and see how it will work.
Yeah, of course, the study, I mean, is not finished here. We have still 1 year until we get to the Dimorphos to go on, and we should complete it with different sizes for the boulders and different distances to study more in detail, which is the role of these boulders on the sun. And so this is just the first step.
Okay. Any more? Yeah. David? Oh, they have their own mic. Oh,
okay.
Okay.
Hello, thanks for the talk. I was wondering regarding DART, what will be the direction of the motion of Dimorphos in respect to the impact of DART? So will it be a head-on impact? Will it be sideways? Because I imagine they've calculated the most likely angle to create a significant deflection. So I was wondering.
Shall you answer that?
Yeah, as you want, or we can both.
We can both talk together.
We can
Well,
ask
anyway, I can say that to make it to get maximum effect on the slowing this thing down, they try to get for a head-on collision to slow down the orbit velocity of the object. They are probably pretty good in calculating these kind of hits. What is not known is how it's going to respond, of course. That's and if it's going to strike maybe at some angle, maybe at one part of it, maybe it's causing rotation or so that is. But the aim is to make a head-on collision there.
So is it a priority to have a change in speed or a change in the angle of the orbit, or is it just to create any significant observable change in general?
What can you?
So is it a priority to have a change in velocity or a change in the angle or the direction of the orbit?
Yeah, well, velocity and the orbit is going to be the diameter is going to be smaller. Okay, so everything will be affected. They are also studying, some working groups are studying even how is this going to affect the spin of the system. Not only Dimorphos, but also Didymos will be probably affected, because everything is at equilibrium, and now we are going to move slightly from this equilibrium, and probably everything will be affected as a whole. But the priority is diminishing the orbit and changing the velocity.
Okay, thank you very much.
Yeah, thank you very much for a very interesting talk. Actually, the previous person raised part of the question I had, but it has to do with the momentum. As we all know, momentum is a vector quantity. So it has two properties, a magnitude and a direction. And so you can transfer both of those quantities upon impact. So my question was, when you talk about large beta, that must refer only to the magnitude, I suppose. And
Yeah.
Does beta have any information about angle?
Yes, it's yeah. When we speak about beta, it's projected all in the same direction. Like how to say? Yeah, the perpendicular to the surface. Okay, so it's everything projected in the same direction. It's a scalar quantity.
And then I think, as you commented, if you hit Dimorphos, for example, on one of the edges, you could induce an angular momentum and make it spin. So that would be, in my opinion, a waste of energy if the
Yeah.
objective
Yes.
is to knock it out of orbit. You don't want to waste energy
Yeah.
exciting other degrees of freedom.
Yeah, yeah. The
Right.
problem is that Dimorphos is not homogeneous, and then we don't know exactly where is the center of gravity. So that's why, like 10 days before the impact, there is a small spacecraft that is coming out from DART, and it will go closer. It will give a couple of flybys to determine which is going to be or likely to be the better place to hit on the Dimorphos, because right now we don't really know exactly, and this must be determined because of the shape also. The shape is going to be also important. So yes, yes. The idea is avoiding spinning, but it could happen.
Thank you.
Okay, and I think we have 2 more questions in the chat. I will read it. From Hector Vives, he says, great talk. I have a question. Does the air in the impact experiments have any effect in the outcome compared to a vacuum?
We have not seen that effect, no, because the numerical simulations assume a vacuum, and we are using 1 atmosphere pressure. And we can also see that we have very little effect from the air on the ejecta movement, for instance. We have very good, almost perfectly straight ejecta curtains and so. But it seems like it's not affecting the at least the comparisons between the model and the experiments much. No.
Okay, and then we have
But
one.
I want
sorry,
to add
sorry.
something, and this is one of the main goals of our work, that we work here with also not only pressure. What about gravity? Because we have here gravity, and in the Dimorphos is microgravity. So the idea is exactly that. We are doing experiments here in the conditions we have here, 1 atmosphere and gravity, in order to validate the codes that can be later on used in other conditions. But once they are validated and calibrated, then we can trust the results in other conditions. So this is the idea of working with both experiments and modeling.
We are not the only ones also doing experiments for these code validations, and so we have colleagues in Japan and so that are working with a little bit other type of experiments, also studying the effect of the gravity. For instance, they have drop towers and things like that to study impacts in lower gravity than what we are doing. So we contribute with our part, and others contribute with their things.
Okay, thank you. And Ithaskun says, thanks a lot for the very nice talk. Is there any way to study the effects of the impacts on the chemical composition of the area that has been impacted with both Hera and with theoretical simulations?
We expect to know, we expect to study these kind of things with Hera. So with the Hera mission, well, this is going to, because DART, the main goal is impacting, so it's not so well equipped with, some very high resolution cameras or things like that. But Hera, the objective is different, it's more scientific, let's say. So they are going to be there, and they are going to get high resolution images, 20 centimeters in resolution, I think. So very, very, very high resolution. And they are going to study composition, to study very well the geometry of the crater, and all these features that we are not going to be able to study with DART, because from Earth, the only thing we are going to be able to see is a change in orbit, and not very much. But with Hera, we are going to study all these kind of things. With the numerical modeling, I cannot tell because with the numerical modeling up to now, what we are doing is just studying the mechanical properties, not the chemical composition or things like that. So I cannot tell about that.
Okay. So no more questions?
Very quick one. Are you going to consider another impact angles in your experiments and your simulation, or just 90 degrees as you have already tried?
Different angles, you mean?
Yes, just in case the mission impact with the asteroid in another angle.
Yeah. I have been so busy with we have been so busy with
I don't know how
with
difficult is
finalizing
that, yeah.
this and the model and the modelers, and so I've been really working on these results. So we will have to discuss with the modelers what the next step will be in the experiment, and yeah, do we have what plans do we have there right now?
Yeah, we have
yeah.
to explore, as we said, different sizes, different distances, or maybe different angles. I don't know.
Yeah, we will see, but
Yeah.
it's not at least not decided before Christmas.
Thank you. Thank you very much for your talk. Very nice.
Thank you.
That's a good plan for the new year.
Yeah.
So
I think we have a long list somewhere. I remember of because we had a brainstorm some time ago with the modelers, and we had a long, like a wish list of all the various things that we wanted to study. We focused on these things to begin with, and I will go back to the wish list and see, but I don't recall exactly now what more things that were on that. But we had a meeting with a brainstorming on what was needed for the validations. So maybe we will test various other things, changing properties of these ceramic boulders, for instance, sizes of these boulders. I think it was on the list that we will use something that has a relation to the projectile that maybe is bigger or smaller, and things like this. Now, yeah, and yeah, depth burial in the target to the one that is crushed, for instance, by the impact. Yeah, you start to recall the list now. The ray formation also, and things like that, because it also affects how the ejecta is moving. It's not perfectly homogeneous in these rubble-pile targets. Not only the ejection angle, but it's also that it is focused. So depending on how boulders are distributed in the target, maybe you get a focusing on ejecta more on one side than the other, and that could theoretically, I think, affect also the momentum transfer. So definitely these boulders in the target affect the ejecta concentration into rays.
So you are going to be busy. Okay, so thank you very much for a very nice talk. And just reminding all the audience that we will be back the 14th of January with the next seminar. So thank you very much.
Thank you.
Thank you.